Hi there, folks. Happy Pi Day to all of you watching. This video just aims to explain a particular problem we covered today in my MathCounts contest training session. We didn't have quite enough time to do this because it is a bit complicated, more complicated than the other problems we worked on today. So as promised, I decided to make a completely separate video covering the full solution to this problem. So it's asking us to determine the ratio of the surface area of a prism to the volume if the length, the width, and the height are zeros of this given polynomial. They want us to express our answer in terms of a fraction. So you might be thinking that we might want to just brute force our way through this one. We have some cubic polynomial. By this point, we're pretty good at algebra. We have all these tricks at our disposal to help us with algebraic polynomials like this one. We have tricks like factoring, completing the square, quadratic formula, but that won't really help us with this one. But it actually requires a bit of a lesser known trick to help us. We're going to need something called Vieta's theorem to help us solve this particular problem. And let's just go over what Vieta's theorem says real quick. So Vieta's theorem tells us the following. It tells us if we have a polynomial function like this with real coefficients, let's call this ax to the third power minus bx squared. Here, well, let me just write everything first. And I will add the exponents. So Vieta's theorem tells us that if we have a polynomial that looks like this, then we have more information about it than we realize. We have more information that will help us solve problems like this one that we're given. So the information that it tells us, first of all, the first thing it tells us that if we have a sum, let's call it S1. I'll put the one a little bit later as a subscript. S1 is just a sum. It tells us that here, I'm not good at typing Greek letters. I know I'm on a Mac right now. There are a lot of special keyboard combinations I need to do. I'm not good at all that stuff, so I'm just going to write them in using the pencil. So our first sum is going to be Greek letter alpha plus beta plus gamma. These are just lowercase Greek letters, alpha, beta, and gamma. And then that is equal to opposite of b over a. And then what else does it tell us? We have even more information to help us here. So we have yet another sum. This time I'm going to make it S sub 2. Our other sum is given by the following. We have alpha times beta plus beta times gamma plus gamma times alpha. And Vieta's theorem tells us that this sum is equal to C over A. And again, C and A are real number coefficients that we really have as part of this problem. This is equal to coefficient C divided by coefficient A. And then the last thing it tells us is that we also have a product. I'm going to just use P for product. Product is equal to the product of all three Greek letters. It's going to be equal to alpha times beta times gamma. And we know that tells us that this product is equal to the opposite of D over A. And you might be thinking, Justin, how does this even remotely help us with this problem? I know it doesn't really look like it'll help, but when we take some fundamental information about our problem, specifically to do with this geometric figure that we're given, it'll become more clear as we go on why this is such a useful theorem, why it's important to know this. So let's start by identifying all our coefficients. So I'm going to look at our polynomial, x cubed minus 3x squared plus 13x minus 15. Really helpful that it's equal to 0. We don't really have to do much manipulation with that one. So it tells us that a is equal to 1. And it tells us that b is equal to negative 3, that c is equal to 13, and that d is equal to negative 15. Good information to have. So I'm going to draw a really, really poor drawing of this figure that we're given. Don't expect greatness from me. You'll only be disappointed. I'd never be able to pass art school. So this is our rectangular prism, and let's see if we can generate expressions for the volume and for the surface area, because we need both of those in order to find our answer, in order to find the ratio. So because Vieta's theorem uses these Greek letters, it uses 3 of them, and because we know that clearly this figure has 3 dimensions, 3 clear dimensions, I think it only makes sense to label them using Greek letters. So our horizontal dimension, I'm going to call that alpha. The one that goes parallel to this direction, I'm going to call that beta. And then we just have one more we haven't done yet. The one going up and down, that is alpha. So we have alpha, we have beta, and we have gamma. So now we want to think of ways we can use Vieta's theorem to help us find the information they want us to find. So let's see if we can create an expression for the surface area. So I'm going to make a new variable, SA is surface area. That's going to be equal to the area of this bottom part plus the area of this top part. So because the bottom and the top are equal to each other, all we really need to do is say that together these two shaded planes are going to be equal to 2 times alpha plus the height. So it's going to be 2 times alpha, no, sorry, alpha times gamma. 2 times alpha times gamma. That will give us the total shaded area between those two. Whoops. And we're going to have something similar for the remaining sides as well. We're going to have, the sides are going to be 2 times beta times gamma. And then our remaining front and back sides of this figure are going to be 2 times alpha times gamma. And you might have made the connection already, why it's useful to have Vieta's theorem in this situation. I noticed that what we have right here looks really, really similar to what we have right there. It looks really similar to the second sum part of Vieta's theorem. So what we can do is we can modify our formula to look more like this part of Vieta's theorem. We can factor out a 2 from everything, and I'm going to be really lazy. I'm just going to do it like this. Don't expect greatness from me or any effort. You'll only be disappointed. So I just took our surface area, moved the 2 out front, and what I'm going to do is I'm going to say this is equal to not just C over A, but 2 times C over A. And we know that C is equal to 13, and we know that A is equal to 1. C over A, 13 over 1. And you might be wondering what the 2 is for, because without the 2, this is totally supported by Vieta's theorem. This makes perfect sense logically and geometrically, but what I'm going to do is I'm going to multiply both sides by 2 in order to have the surface area, because without the 2, we only have half of the surface area. We need to multiply both sides of this formula from Vieta's theorem in order to have the true surface area. So this is not 2 and 13 over 1, where this is 2 times 13 over 1. All right, looks good so far. And then we also want to do something similar for the volume. So we know that the volume is just going to be the product of our 3 dimensions. So V is volume is just alpha times beta times gamma. And conveniently enough, we know that's going to be equal to just the opposite of D over not the opposite of A, just the opposite of our coefficient D over coefficient A. So this is going to be negative D, and D is negative 15, so this would be negative 15. All that divided by what we have for A, that's just going to be 1. So if we were to simplify things, our surface area is going to be 2 times 13 over 1. That simplifies to just 26. So we have our surface area is equal to 26. And then we have the volume as well. The volume is just 15. And to be honest with you, this seemed a lot more complicated than it really is. Vieta's theorem really helped us tremendously, and it's a really good thing to have in your mathematical arsenal. It's good to know how to manipulate cubics like this in order to produce an accurate, efficient result. So what do they want from us? They want us to express the answer as a common fraction. It should be a ratio of the surface area to the volume. So it should be a fraction with the surface area on top and the volume on the bottom. So we have SA divided by V. That is just 26 over 15. And that is our final answer. I hope you found this helpful, and I hope you were excited about this as I was. I had a blast doing this, and I hope you did too. All right, folks, happy Pi Day, and I'll see you in the next video. Adios.